Bienvenue! In our last lecture, we covered how to balance the half reactions, the reduction and oxidation half reactions, for a redox reaction. But how do we know which way the reaction is going to occur? So, for example, if you have a solution, let me change to a brighter color. If you have a solution of, say, lithium nitrate and a bar of lithium metal hooked up with a bar of copper metal in a solution of copper nitrate. If you mix them together, or you hook up a wire so that they can react sort of at a distance, which way is the reaction going to proceed? Is it going to be lithium ions turning into lithium metal, or copper metal turns into copper ions, or will it be copper ions turning into copper metal and lithium metal turning into lithium ions? This is not something you can predict just by looking at the elements involved. You need the activity series. In this particular case, activity means which element wants to be oxidized, or how much an element wants to be oxidized. Chemical activity can mean different things in different situations, but in this case we're talking about chemical activity and the activity series. Which element wants to be oxidized more? So we have an example of an activity series over here on the right, showing a bunch of elements. And it has lithium up at the top, down through potassium, barium, calcium, blah, 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 all the way down to gold down at the bottom. It has hydrogen in the middle. Hydrogen is not a metal, but that's because the way they originally set this list up, they decided to use hydrogen as a 0 point, because you can't measure any of these things in isolation. They always have to be measured against something else. But by saying that hydrogen is just an arbitrary 0 point, you can compare all the things on this list to hydrogen, and then that gives you a nice list. And you'll see that lithium on this particular list is all the way up at the top. It is the metal that most wants to be oxidized. It wants to lose its electrons more than anything else on this list. And down at the bottom you have gold. Gold is the least active metal on this list. It really, really does not want to lose its oxygens. It wants to stay as gold metal. So that might be one thing that can help you remember what chemical activity means here. If you look down at the bottom of the list, you'll see copper, silver, mercury, platinum, and gold. Those are the jewelry metals, the coinage metals, the noble metals. They really don't want to be oxidized. They're good at staying nice, pure, solid metals. Whereas up at the top, you have lithium, potassium, barium, calcium, sodium. These are the metals that if you drop them in water, they light fires. They're very, very highly reactive. So that is one way to remember and understand the activity series. So the way you use the activity series for a problem like this is you say which element wants to be oxidized more, and you look and you'll see copper is down at the bottom just underneath copper, and lithium is all the way up at the top. It really wants to be oxidized. So the chemical equation that shows lithium being oxidized is going to be the correct one. A chemical equation that shows copper being oxidized and lithium being reduced is wrong. So that means that this reaction up top is wrong. Lithium is going to end up in its ionic form. The correct one is down here on the bottom. Lithium is going to be oxidized, copper is going to be reduced. Or to put it another way, lithium is the reducing agent, And copper is the oxidizing agent. Lithium wants to be oxidized so badly, it's going to force its electrons on copper, pretty much. They're both metals. They both react by losing electrons. So even though copper, it doesn't want much to be oxidized, it wants it a little bit. But lithium wants it so much more that it's going to force its electrons onto copper. That is how the oxidation series, or the activity series, works. If it's higher on the list, it wants to be oxidized, and it will force the other to be reduced. If you compare, say, magnesium and iron, or, let's say, calcium and barium, which one is going to be oxidized, which one is going to be reduced? The way you solve that is by looking at the list. Which one is higher on the list, magnesium or iron? You just start at the top and you work your way down until you find one of them. Here we go. Here is magnesium. Come further down, and here's iron. So that means that for this particular list, it's not a very big list, it's not a very comprehensive list. Magnesium going to magnesium 2 plus is higher in activity than iron going to iron 2 plus. So notice that the iron in this case is going to iron 2 plus, not to iron 3 plus. Iron going to 2 plus and iron going to 3 plus are two entirely different half reactions. They have different activities. And you can even get the activity of iron going from 2 plus to 3 plus. So be careful that you're looking at the correct spot on the list. So that means magnesium is higher, so magnesium is going to be oxidized, iron is going to be reduced. And so it's going to be magnesium plus iron 2 plus goes to magnesium 2 plus iron. This was calcium and barium. So we look at the list for this one, and you have calcium and barium. Oh, they're both right up there at the top, right next to each other, but barium is above calcium. These are both alkaline earth metals, so they're both going to a 2 plus charge. Barium is higher, calcium is lower. So it's going to be barium plus calcium 2 plus goes to form barium 2 plus metallic calcium. I want to stress that this is applicable to a setup like the one you see up top, where you have a metal immersed in a solution of that metal's ions, and another metal immersed in a solution of that metal's ions. A battery is what we're looking at here. That's when this sort of activity series problem would come up. Now, like I said somewhere earlier, redox reactions are not a particular kind of reaction. They're a class of reactions. There are multiple kinds of redox reactions, or I should say, different kinds of reactions can be thought of as redox reactions. The one we were just looking at, the two metals being reacted against each other, one ionic, the other metallic, that is an example of a galvanic reaction, or a voltaic reaction. It doesn't have to be two metals. It often is. But that is the setup that you see here. A metal and its ionic compound being reacted with another metal and an ionic in its ionic compound. Now, the thing is, this is not quite complete. Because this right here, first off, this is an example of a battery. Very simple, very straightforward battery. You may have heard of lithium acid batteries or lithium ion batteries. That's what they're talking about, lithium and lithium ion. So this is a battery. We have electrons moving along the wire going from from lithium to copper. Because lithium is being oxidized, that means it's giving up electrons. Copper is being reduced. It is receiving those electrons. Its charge is going down. Which means that lithium is leaving the metal and entering solution, and copper ions are depositing onto the metal over here. When you first hook up this battery, if you had, say, a voltmeter of some kind, boom, bing, the little needle here would twitch to the right and then immediately go back to 0. Reason for that is fairly simple. You send a few million electrons from one side to the other, you build up a negative charge over here, you build up a positive charge over here, and suddenly the electrons stop flowing. You need some way to balance out the charge between the two halves of the reaction. And the way you do that is not by hooking up another wire. That would not solve the problem. What you need is something like this. That drawing here is going to be particularly crude. This is what's known as a salt bridge. Because instead of letting electrons flow, it lets ions flow. Positive ions can flow from one side to the other, negative ions can flow from one side to the other. So that allows the charges to balance out. And, we have electrons moving from left to right, so that means that our negative ions are going to need to move from right to left, and our positive ions are going to be moving from left to right. Between them all, the negative and positive ions moving in that way is going to balance out the charge buildup from the movement of electrons. And that's how you're going to get the complete circuit. You need to complete the circuit for the battery to work. So that is an example of a galvanic cell, or a voltaic cell. Those aren't actually the same thing. Galvanic cell is a spontaneous reaction. A voltaic cell is when you apply a voltage from the outside in order to force the battery to run backwards. All right. Other kinds of reactions that might be redox reactions are combination reactions. Carbon plus oxygen make carbon dioxide, for example. Decomposition reaction, calcium carbonate decomposing into calcium oxide plus carbon dioxide, for example, might qualify, might not. And combustion is another reaction. Combustion is fairly popular because you can break combustion up into several different components or several different steps to try and isolate the various oxidations and reductions that are taking place. That is how a fuel cell works, for example, a hydrogen fuel cell that they're trying to make for electric cars and so on. It's essentially a combustion reaction that has been split up into several parts, so that instead of combining hydrogen and oxygen and getting an explosion, you combine them more slowly to get electricity instead of an explosion. Doing it that way is far more efficient than just blowing things up. Blowing things up is fun, but inefficient. In all things, it's fun, but inefficient. Except on the 4th of July. And it's fun, and that's the point, so that is perfectly efficient. Precipitation reactions, or double displacement reactions, do not involve redox. No charges are changing. Okay, all you have is two things combining that are insoluble, and so they fall out of solution, but oxidation numbers have not changed, not redox. Not all of these different redox reactions are really amenable to the half-reaction method, meaning that the half-reaction method will work for these galvanic reactions, where you can separate them into two half-reactions quite easily, but otherwise they might not work so well. It can be particularly difficult when a single species is both oxidizing and being reduced. Just some things are strange like that. And that does it for redox reactions and for this lecture. When we come back, we'll move on to discussing concentration, titration, pH, and a couple of others.